and welcome to the very first virtual event of the San Francisco Microscopical Society. Thanks so much for joining us, and welcome to all of you joining us here on YouTube, watching from all around the world. I'm really excited about tonight's event and really excited to welcome all of you. We have a really fantastic, wonderful event tonight, Microscopes for Space Exploration. It's a really geeky topic, and I'm really excited to geek out with all of you. The San Francisco Microscopical Society is a focal point for people who use microscopes for all different types of reasons to be able to connect and learn new things from one another. Space exploration is one of those things that people don't always associate microscopes with, but microscopes can be really useful for space exploration, it turns out. So if you don't know me, I'm Ariel Waldman. I'm the president of the San Francisco Microscopical Society, really fantastic nonprofit here in San Francisco, and we're just doing a lot of really exciting work with it. And my sort of story of how I got involved in the San Francisco Microscopical Society began with Antarctica. I was applying for a grant, the National Science Foundation's Antarctic Artists and Writers Grant, where they send artists and writers to Antarctica to do a bunch of awesome stuff. And I was teaching myself microscopy in order to film the microscopic life underneath the ice in all of the different exotic and faraway places in Antarctica. But I found that I really could have used a community to help me learn and help push me to get even better at using microscopes and just have a really great group of people to connect with. And so the San Francisco Microscopical Society actually helped me in my journey, and I was able to go to Antarctica to film all of the little creepy crawlies underneath the ice there. And this is what I really love about the society, is that it's really inclusive of people at all different stages and all different disciplines, be it the arts or the sciences, be it your first microscope, or maybe you've been working with microscopes for decades. So the San Francisco Microscopical Society has actually been around for quite a while. It started out in 1870. So last year, we actually had our 150th anniversary of the San Francisco Microscopical Society starting. This is what the rooms in the society actually used to look like. And I don't know, it's just really fantastic to be part of something that has such a long and rich history. So our website is sfmicrosociety.org. As mentioned, we're a community of amateur and professional microscopists, and our mission is to be a focal point for all microscopists across all disciplines, both science and the arts. And we welcome people of any age or background, from those who have not used a microscope to those who have been working with them for decades. And we actually have a membership program. So if you would like to become a member of the San Francisco Microscopical Society, you can go to our website. You probably see a banner on the YouTube video now with where you can go. And membership is only $12 a year to be a member and a part of this community. Also, if you're a student, you can get your first year free if you just shoot us an email. We'll set you up with that. And our in-person activities and resources are primarily focused in the San Francisco Bay Area, but we welcome members from any location and offer virtual opportunities like this one to connect. So it's a really fantastic, geeky group of people that I hope you'll consider joining. And we're also a 501c3 nonprofit. So if you're interested in donating to the Microscopy Society or getting involved or volunteering, absolutely get in touch. So with all that, as I mentioned, we have a really awesome event tonight. And to me, I really like the idea of microscopes for space exploration, because microscopy is all about orders of magnitude, right? So microscopy is all about looking at really, really tiny things. But tonight's event is kind of about how using tools that are made for studying incredibly tiny things can connect to our huge cosmological expanse. So going through those orders of magnitude that you can use microscopy to access. So we have a couple of really awesome speakers tonight who I will let introduce themselves. And after they both speak, we'll be doing Q&A with all of our speakers at the end. So at any point, you can go onto the YouTube live chat type in any questions you have, comments, anything along the way. And at the end, after both of our speakers give their presentations, we will do Q&A and we will pull in questions from the YouTube live chat. So feel free to ask questions along the way or at the end, and we will pull them up. So without further ado, I'd like to bring on our first speaker, Scott. Scott, welcome.
Hi.
Thanks so much for being here.
Thank you for having me.
I'm really looking forward to your talk. I don't want to spoil it. So I'm going to just let you go ahead and take it away. If you want to go ahead and hit play on your presentation.
Perfect.
And I can see your slides and they look awesome. So please go ahead and take it away.
All right. Thank you so much. I appreciate it. Super happy to be here. This is going to be hopefully entertaining for everybody. Thanks for joining us tonight too. Hopefully everybody is safe and healthy. I'm going to be talking about micrometeorites. They're pretty much just an obsession of mine now. But let me get out the boring part. My name is Scott Peterson. I'm a father, a husband, a veteran, an amateur scientist, a student, basically probably for the rest of my life, and a micrometeorite hunter. So I'll kind of get into a little bit more. I think we'll just kind of, the best part of the micrometeorites by far is just how they look. So I'm going to go over a little bit of the history, a little bit of where they come from, why they look the way they do, but then I'll just get into the best part, the pictures. So what are micrometeorites? Micrometeorites are the boring answer. A micrometeoroid that has survived entry through Earth's atmosphere. So we'll get a little bit more into it and have the beautiful pictures come a little bit later. Hopefully you'll stick around for that. The classification, you might already know this, but the rock that is in space is a meteoroid. Once you see that flaming thing in the sky, that's what we call the meteor, and it's only actually a meteorite once it touches the ground. And we got a nice little GIF here as well. So where do they come from? There's a lot of different options. There's a lot of different possibilities. We don't necessarily know the origin yet, but comets are possible origin, such as this one, Comet 67P. This is actually a video of on the comet surface. It's pretty amazing, not just because it's on the comet surface, but actually because in the background you can see the stars moving. You can see the dust particles that are on the comet itself, and then you can see the cosmic rays that were hitting the sensors of the camera. Interplanetary dust cloud. So everywhere in between basically Mars and Jupiter, there's a bunch of stuff, and that might be where some of them come from as well. And through the asteroids, such as this one, Vesta. Beautiful image of one. So micrometeorites, they come in at the atmosphere around 7 miles per second. And I don't know about you, but that seems a little hard to even comprehend. So it's really, really, really quick. And that's where they heat up. But at 7 miles per second, that can do a lot of damage. And this is actually a little bit slower than that, but it has a little bit more energy going into it. But you got to worry about things like your satellites or the International Space Station. And here's a picture of the International Space Station. Again, super fast if you think about it, traveling at 17,000 miles per hour, but compared to the micrometeorite coming in, it's basically standing still. In 2010, they added the cupola, and it's just the amazing place where the astronauts come up. And I heard that they had to really go immediately and just kind of check out their views. But they can also hear little dings, and those dings are the little micrometeoroids. So you have to protect it. This is also for cosmic rays, but the windows on there needed to be protected from the little micrometeoroids that come in. So shapes and sizes. They kind of range from unmelted, where they don't really heat up that much during entry, all the way to completely melted glass. And there's a lot of reasons that will cause those. The angle that they come in, the speed, the rotation of the Earth can even have an effect on what they will end up being, how much they'll heat up. So here's kind of the temperature range of what they'll be. Unmelted on, obviously, on the lower right. Glass heating up all the way to 2000 C. So where have they been found? One of the first places was a long time ago at the Challenger expedition. These guys were doing pretty much amazing work, and they didn't even know they found them at first, but they collected little spheres off of the seafloor bottom. One of my favorite places, Ariel probably understands this one, is the South Pole water well. So the researchers down there need to drink water, obviously, and they'll melt the snow underneath them. And as they melt that snow, the particles that are in that snow will fall to the bottom of the water, and basically a bunch of amazing scientists vacuumed up the material, which was all micrometeorites, and they got a lot that way. Another great method is just going along a mountain ridge. As the ice moves towards the mountain and the wind pushes them all, they kind of accumulate in one area. They fall everywhere. They fall all over the world. There's no one hot spot or anything like that. So over time, they can be found anywhere and fossilized through sandstone. And now what was once thought impossible, we can find them in cities like I do. So what is the process for me for finding the micrometeorites? First thing I do is basically just look on Google Maps or Google Earth, or I have my son do it, and we'll try to find the best suitable roof. An old, flat vinyl roof with barriers is helpful. A lot of universities or schools or churches are really great. If they allow me, I usually send out probably like 100 emails a year, and I'll get maybe like 10 to 20 guesses. But if they allow me up on the roof, I'll go out to the low-lying areas, like in this photo, anywhere that the water or rain or wind has brought the micrometeorites, and spend as much time as possible just collecting as much magnetic material as I can. And then I'll take that stuff and I'll put it into a mother bag, and then I'll bring it home. And you're probably saying, Scott, that's not your home. You just found that on the internet. I disagree, but let's move on. So once I have all that material at my smaller house and that, I will just clean all the material, and I'll put it in a bucket just like this, and all of the organic material and all of the really smaller than micrometeorites material will float to the top. So I just pour that out continuously until the water becomes clear. And once everything's cleared out, I'll either let it dry or I will wet sieve it, and I'll put it through the sieves. And this is great for a couple of reasons, just because it'll get rid of anything that is too small or too big. But it also, once I'm looking underneath the microscope, everything's on the same plane. So I'll let everything dry, and then I'll start looking at it under the microscope. And this can take a long time. When I first started, it would take a week, 2 weeks to find anything. Now I've kind of got it down to a relaxing process where I can usually find them right away, but it takes a while. And since we're here talking to you guys, I have a Olympus BH2 BHS and custom stack shot, gooseneck lighting, old wonderful one that I put an LED light in, a 3D printed diffusers, just kind of tame down the light, and a Nikon D5200 that I will probably upgrade to something else eventually. Once I have the micrometeorites or the possible candidates that I think are micrometeorites, I'll bring them to the University of Minnesota's probe lab, and that is an amazing place. This is actually the old one that they had, and now this is the new one. Here we can do almost anything. It's almost endless for the possibilities that we can do. One of the amazing things is we can figure out for sure if they are micrometeorite. Most micrometers will have the same chemical makeup. They're high in oxygen, magnesium, and silicon, just like this. And if I see this, then I know it's a micrometeorite. It's an echo of the early solar system. So what do they look like? There's some little images here and there, but once we get into it, you'll start liking them. So they're tiny, right? They're around 0.2 to 0.4 millimeters. and that's tiny. It's hard to grasp when you're trying to think about how small they actually are, but they're pretty small. And here's a picture actually from my friend John Larson. Here's a barred olivine. Here's another barred olivine with a beautiful bead. Here's a cryptocrystalline. And another cryptocrystalline turtleback. This is actually the second micrometeorite I ever found, and it has the nice metal bead there as well. Here's a glassy one with those metal beads sticking out. Another beautiful glass one. This one might be, I'm going to say this every time, but one of my favorites. Here's another glassy one. And a porphyritic. You can see some of those crystal formations on there, and how this is kind of a good image because when I'm looking at them underneath the microscope, they seem almost wet, the shininess of the glass on top of them. This one also might be my favorite. And there's transitional parts where one side might seem glassy and the other side is barred olivine. Or the top might seem like a cryptocrystalline and the bottom is glassy. This is an interesting one too. And there's new, strange types. There's this one, I don't even know what really to call it, but I think it might be kind of oriented, and then the back part might have came off. And same with this one, you can kind of see that maybe it was heading in one direction and the back was kind of vacuum and pulled that back part out. And then there's the unmelted types. I haven't actually found one of those yet. I have these images from a friend of mine. And so at that scanning electron microscope, you can get some pretty detailed images. And here's another barred olivine with that metal bead. And you can see there's one next to it that has escaped. The porphyritic. Beautiful glass one from a friend of mine in Norway. The porphyritic, you can see it's almost the opposite of that glassy one with all those ragged edges. So as small as they are, I've been able to polish them in half. So what you're seeing here is the inside of one. It's pretty hard. It's almost like cutting it in half, but it's really just kind of sanding it down until you get to the middle of it. Here's another one. This one will be pretty interesting in 2 more slides. So also what we can do at the probe lab is do elemental mapping. So I'm thinking the first one on the top left, that's one for oxygen, where the colors are more bright. That's where the oxygen is more, there's more of it in that location. So this was the one of that picture before. This is pretty remarkable. This is actually a micrometer that's been polished on both sides. So what you're seeing here is this was under my microscope, and I had the cross-polarized light coming through it. So everywhere you're seeing here is actually just, it's see-through. This one as well. You can see the difference. So the one on the right is the original SEM image that I have of it, and then the one on the left is the one with the polarized light. Pretty amazing. Here's just a little perspective how we can get down deep into them. As small as they are, I'll keep saying that. They're so small, but we can get down deep into them and see the crystal formation, such as this. And more beautiful crystals. And there's a large bead, the crystals forming around it. The SEM images are so great. I've been trying a long time to get my images as good as I can. So here's one, and you can kind of see the zoomed in part. Here's another whole barred olivine in the zoomed in area. This one was actually found on the bottom of Lake Michigan. And so the sizes, most of them are around 0.2 to 0.4, like I said earlier. The one in the middle here is around 0.3. The one on the far left is my smallest micrometer that I've ever found, around 0.07. And the one on the right is the biggest one that I've ever found, around 1 millimeter. So they're probably asking what are the scientific contributions that they're basically endless. There's not that much we know about micrometeorites. There is a lot, but there's still so much to be learned. Origin, again, like I was saying earlier, is a big thing. One of my big things is just trying to disprove the idea that micrometeors are anything that are small, magnetic, and spherical that you find on a roof. So when you first start looking, you're going to find things like this. A lot of times people will email me and they'll think that these are micrometeorites. They go, "Oh, I found a micrometeorite," and then I have to break their heart and tell them that these aren't. A lot of times they're from grinding wheels or power tools, fireworks, or even the reflective road paint. The little things on them I find those all the time on roofs. Here's some fun images just to kind of end it up. Those sieves that I was talking about earlier. Here's a micrometeorite resting on one of those sieves, so you can kind of see that it won't fall through and it'll stay right there. My little buddy spider holding one. And here is one on a butterfly, actually a moth wing. So I'm sure we'll have more questions later. I probably could add a million more slides and talk for a million more hours about micrometeorites. But if you have any questions, we'll get to some of those later on. But you can also visit my website and feel free to email me there. Or if you want to Google Scott Peterson micrometeorites, you can do that. Don't just Google Scott Peterson, because that'll bring you to a different thing. So thank you so much.
That is awesome, Scott. Thank you so much for presenting. One thing you always do is you make it look effortless, all these beautiful images that you have of micrometeorites. And I will say for the audience listening in, Scott sent me one micrometeorite to test out, taking photos of it. And I quickly learned just how much work he puts into making those beautiful images, because I could not make one very easily at all.
I appreciate it. Yeah, it takes a lot of work.
Yeah, so awesome. I hope a lot of people check out your website, and we will bring you back after our next talk to do Q&A. So if you have questions, feel free to add them in the YouTube live chat now, or you can wait until the end when we go to Q&A. So thanks again, Scott. I'm going to bring on our next speaker, Jay. Hey, Jay. And Jay is calling in. She's always doing awesome field work. So it's Jay collaborating with Chris. We're keeping Chris backstage in control of these slides. Jay, welcome.
Thank you, Ariel. Thanks for the invite. It's great to be here. I'm calling in from Klamath Falls, Oregon, where we're looking for microbes.
Awesome. Well, I can see your slides. Everything looks great. So feel free to go ahead and take it away.
Good. Thanks so much. So the idea here is to talk about a specific microscope that my group, in collaboration with others, has developed for looking for life, microbial life specifically, in extreme environments. So the big picture is, like Horton, can we see signs of life that other people just cannot see? Signs of life that are only microscopic in extreme environments where only microbes live. So imagine a world where there are only microbes. Imagine a world where there are no fish or squid or sea turtles. Everything is just bacteria and things similar to bacteria. How would you see them as life? Certainly we know that all life has to consist of cells, but in order to see those cells, you need to get a microscope. Sometimes the structures these cells make are large, but we really don't know they're alive until we zoom in and see them doing lifelike things. Next. So places we're really interested in looking and that we're developing the microscope specifically for are the so-called ocean worlds. So these are moons of Jupiter and Saturn, as well as planetary bodies such as even Pluto, that have an ice crust and underneath a liquid water ocean. So there's a variety of evidence that suggests that places like Europa, Next, and Enceladus, which is a moon of Saturn, contain this liquid ocean with a rocky core that provides all of the minerals and other elements that life needs. Now you can see that this artist here hopes that there are squids. We're just hoping for something much smaller than squids, but how are we going to see them? Next. If there were bacteria there, how would we find them? So on Earth, we just look now with microscopes. That's really the gold standard, and you can see these beautiful pictures of organisms taken from various environmental locations. You can stain them with a single stain. In the left case, this is DAPI. In the right-hand case, there's DAPI plus another stain called FM143 that stains different parts of the cells. It helps confirm that these things are actually alive because they contain multiple elements that suggest that they are a cell: lipids, nucleic acids, and then this repeating consistent structure that doesn't look like minerals, that doesn't occur randomly, and that just has this pattern of a systemic form of life. Next, please. But the burden of proof on Earth is low. If you say you have 10 to the 9th bacteria per gram of soil in your backyard, nobody cares if it's really 5 times 10 to the 8th and not 10 to the 9th. Nobody's going to laugh at you. You're not going to be a crackpot. Try saying it on Mars, though, and it's a different story. We know what the Earth chemistry is. We know how to stain for lipids and DNA and enzymes. And the other thing is that microscopes are big and heavy, and usually they take an expert operator. So how do you send something like that to another planet? Next, please. Even on Earth, with all of this, there are still life detection problems and things that are really controversial. So up in panel A, you see these structures that are possibly nanobacteria, but might even just be minerals that occur in naturally in parts of the body where there tend to be crystals, such as in the teeth. And so there's some people who suggest that these nanobacteria are the cause of things like gum disease and kidney stones, but it could just be that they're actually tooth crystals or parts of minerals excreted by the kidney that naturally occur in the body and not organisms at all. And there's a lot of controversy about it because every type of microscopy you use on these organisms is somewhat ambiguous. So imagine taking these images back from another planet. You would have decades of arguing ahead of you and no real solution. Next. So what we would like to do is see something actually alive, something actually behaving the way life behaves, because we don't have a chemical definition of life. We don't know exactly a physical or chemical definition of what distinguishes chemistry from life. So basically, it has to swim up and bite you. And so we just have to watch it swim up and bite you on the micron scale. Next. So when you go to places like the Marianas Trench and you want to see something like whether there are fish that live down there, you basically bring a severed fish head on a stick and you bring it down to the trench and you wait till things appear. So this is the gold standard on Earth. So now we want to do the same exact thing, but on the micrometer scale. Micrometer fish head on a stick. What's that? Well, simple amino acids. And simple amino acids are known to exist in interstellar space. They're known to exist on Mars. They're known to exist pretty much everywhere we've looked. So in this particular case, you can see a capillary tube filled with L-serine, which is a simple amino acid, and these microbes just swarming to it in the exact same manner as the fish head on a stick. So we could imagine that any microbe in the solar system might like this exact same amino acid. Next, please. And so we've built a microscope that doesn't require focusing, that's pretty robust, that we can take to a lot of extreme environments, and we're hoping to be able to take that one day to another planet. Next. So it's based on the principle of holography, or off-axis holography, which is an interferometric technique that uses the interference of light from a beam that is just your reference beam and a beam that is interacted with your object in order to create a pattern of interference fringes on your camera. If you look at that, the Fourier transform of that, you will get a real image, R star O, a virtual image, RO star, and a so-called DC term that you don't care about. You can select your real or virtual image in Fourier space, transform it back, and have an image of what you took in 3 dimensions. Next. So what's great about it, there's no moving parts. You don't have to focus. Imagine focusing with an hour of light speed delay. It's going to be difficult. You end up with over 50 times more depth of field than a standard microscope because you can reconstruct your hologram plane by plane throughout the depth of the sample. You can see things without using dyes by using phase contrast. So it's sort of automatic bright field plus phase contrast. And built-in compression, because if you haven't reconstructed yet, your image is really quite small relative to the amount of information that it encodes. Next, please. So you can track bacteria. Here's a phase image of bacteria swimming around. You can track them through X, Y, and Z. Next. And so what we've done is take a fieldable version of this instrument, packaged all up with a computer and electronics and inside a pretty rugged box so we can stick it in various pieces of ice and whatnot. And we've taken it to all the places we can possibly think where there might be organisms that people don't know really if there are active microorganisms. And we say, well, is there anything there that swims? Because no one has been able to answer that question. Amazingly, there are many places on Earth where we've never been able to say, Are there swimming microorganisms there? And a lot of times people will dogmatically say, oh no, there's nothing there. Everything there is dead. And we're there to prove them wrong. Next, please. So one place is sea ice. Sea ice contains this network of channels, and there's brine inside those channels, and there's organisms in there. So this is not seawater. This is the intact ice. Brine from the channels leaks out if you cut a hole in the ice, and we can put it right into our instrument right there in situ, so the organisms don't have a chance to die before we look at them. Next, please. So there's always something that swims everywhere we go, no matter what the extreme environments, hot, cold, dry, wet, freezing, there's always something that swims. Next, please. And so we're trying to go to more and more extreme places, such as the last remaining ice shelf in Canada, the Milne Ice Shelf, just before it melts. It may have melted last year, who even knows at this point, and see if there's any place where there's something that doesn't swim, because so far everywhere we've gone, there's been something. Next. So here's just an example of glacier ice from 80 degrees north in Canada. If you pick up a piece of ice from the glacier and you melt it overnight, you will see these lovely organisms swimming all around like crazy. I love this video because these things are just so fast and so clear, and they just zip back and forth. And this is the typical appearance of your holographic image. So you can see these airy rings, these patterns of rings around all the organisms that tell you where it's located in the Z-plane. Next. We've also gone to Alaska, up to the town formerly known as Barrow in 2017, 350 miles north of the Arctic Circle, to look in a variety of environments up there. Next. Including sea ice, so 10 to 15 miles out to sea from the coast. The ice was 1.2 to 1.5 meters deep. You dig brine cores, and again, you get seepage of brine out of the ice core. This is not down in the ocean, but in the ice above it. Next. And so here's just examples of the sea ice brine. And you can see some things way out of focus, some things slightly more in focus, but there's definitely stuff zipping around, things of different sizes. Next. And if the things are not as swimmy as you like them to be, or you want them to make them do other things, such as swim to your fish head, you can encourage them using amino acids or sugars or electrons, or even by killing everything in the solution and getting everything else to then come and eat it, which we call induced cannibalism. Next. So the next goal is to go to one of these icy worlds, maybe Europa, maybe Enceladus, maybe somewhere else entirely, maybe the clouds of Venus, and to try to get some samples of something, probably ice, melt them and look at them. And so the real question is where to go, how much to melt, how long to look, how to stimulate it, and what to send back in terms of data. And all of those are huge and open questions, which we're currently working on. Next, please. So we have a quite large team here of people at JPL, Caltech, PSU, and formerly of the University of Washington. And they're the group who led the expedition to Greenland. So a lot of people are working together to try to answer all of these questions, so that when we send a mission to another planet, we have a good idea of what we might see, and we don't waste our time and have to go back multiple times. So that's my talk, and I'd be happy to take any questions.
Awesome. Thanks so much, Jay. I love your work so much. As you know, I've gushed about it to a lot of people, and I just love the idea that, it's completely possible that we might, put a microscope on a spacecraft, send it to an icy moon, and look and see if anything's wiggling around. There's so much that we don't know. And for some people, they might be like, oh, no way. But it's still a possibility. And I think microscopes can be a really fantastic tool for that.
Yeah, what's so amazing is that they're absolutely standard on Earth, and pretty much every biologist has one, but we've never sent one to another planet, not with the resolution that you need to see bacteria. So someday.
Absolutely. So with that, we're going to start Q&A. We're going to bring on Chris and Scott, and going to allow Chris to briefly introduce yourself, since you haven't been on screen yet.
Oh, yeah. Hi, I'm Chris Smith. I'm a system engineer at the Jet Propulsion Laboratory, and I work closely with Jay on building the microscope and getting it into the field.
Yeah. So thanks all of you for tonight. This is just, I don't know, my mind is just going in a million different directions of cool things. I will go ahead and start with a question I have for all of you. And for those of you watching on YouTube, feel free to type your questions into the YouTube chat. We will get to as many as possible. So my question for all of you is about, microscopes are this great tool, not only for looking at all this cool stuff, but also to take you to really interesting places in the world. I think all of you discussed, going to different locations to look at cool things. And I wanted to ask, where is somewhere you haven't been that is high on your list for looking either for micrometeorites or for looking at new microbes? Where is somewhere you'd like to go that you haven't been yet? Scott, I'll start with you.
It's actually a hard question because I want to go everywhere. It's funny. I'll watch a movie and I'll see a roof on there and I'll be like, "Ooh, I want to go in there." Or I'll just be driving by and I'm like, "Nah, that could be a good roof to go on." So really, I'm everywhere. I want to go everywhere.
Rooftops everywhere. Do you want to find micrometeorites in any of the snowy places? Or I guess that's kind of almost really difficult, isn't it?
Kind of. Yeah. Well, I live in a snowy place, but not like that. I want to be able to melt the ice and then find them that way. So that's kind of the goal for the next few years. But yeah, everywhere.
Chris, what about you?
So I actually got into this because Jay wanted help getting an instrument she had to work on Heiberg Island. And I still haven't been there, but that was what motivated me to get into this in the first place. And so I'd really like to go to Heiberg and check out there and look at stuff, and then also to the South Pole. So I really want to visit both North and South Pole.
Yeah, South Pole is on my list. Jay, what about you?
I really want to go to the Milne Ice Shelf. It's the last ice shelf in Canada, and it's going to melt if it hasn't melted already. And I haven't been there.
Awesome. Yeah. So those of you watching at home, if you haven't gotten into microscopes yet and you want an excuse to go exploring places, microscopes are a fantastic excuse to start that. So with that, I'm going to let Matt, who's our AV guy backstage, choose some questions from the YouTube live chat, and we will just see what he picks out and go from there. Some of the questions might be for some of you, some of them might be for all of you. So starting with Eric Weinstein's question, are you able to backtrack and trace a micrometeorite to a known astronomical event? Do you have any pieces of Halley's Comet?
That's a great question. So far, no. Just from where I find them, I have to have it be a completely clean surface and then have that known event happen and then try to find the micrometeorite then. So there's a lot of barriers to that, but it's something on my list to try and do. But I don't know if I mentioned this before, but so micrometeorites, they're small in space. When a larger meteorite, the ones that we're used to, or a meteor, when they come in, they'll leave off little ablations. Those aren't actually, even though they're from outer space, those aren't micrometeorites. So I also need to find those, but it would be pretty amazing to find pieces of Halley's Comet.
Awesome. Thanks so much for your question, Eric. We can go to our next question. All right, from Mike, do you need to have the liquid extracted from the sample, or can you use the digital holographic microscope to look at the brine micro pockets in the ice directly?
That is a great question. We have to get the liquid out of the sample. We can't currently look through ice. And so if you melt the ice, the microorganisms in the brine channels will die from the osmotic shock. So we have to let the liquid seep naturally out of the cut brine channels, and it takes a long time. So it takes an hour or more to actually get enough liquid to look at. Fantastic.
All right, next question. We'll just keep going through these. From Wesley, I know Wesley. Hey, Wesley. With how small they are, I wonder if the crystal structure represents what was formed in space or formed after entry/impact. Scott, I believe that's for you.
Yeah, so when they're coming in space or coming up to the atmosphere, and then they'll melt completely. And then during that process, after they are either liquefied or just partially liquefied, that's when the crystal structures will start to form. So no matter, unless it's one of the unmelted types, no matter what it looked like before, it's completely different after.
Chris was just talking to us backstage that he has a vinyl roof and wants to go sweep it off and wait for meteorites now. Scott, do you have any tips for Chris?
Just start doing it. Get magnets and go do it, and then let me know how it works.
Yeah, I might try that. I could probably put magnets in front of the gutters.
Yeah, absolutely.
Yeah, just catch them all. All right. Do we have any other questions from YouTube? All right, Lena, question for Jay. What optics do you use to generate your interference at the camera plane?
That's a really terrific question, Lena, and it's kind of the bane of our existence. We have to use very simple optics so they can fly. And complex compound objectives, such as the kind you just buy from Nikon or Olympus, are usually, they have multiple lenses glued in place. They wouldn't survive flight. So we just use really simple A-spheres. They're made from a company called Asphericon, and the highest numerical aperture A-sphere that they could possibly make. So we've spent a lot of time and energy talking to companies saying, can you please make us A-spheres with slightly higher numerical aperture? And they cannot. So our NA is about 0.38. It's about as good as we can get. And that really does limit the resolution of any instrument we can send to space.
Great.
And I'll just add one thing to that is we've got a bunch of open source papers, so you don't have to have special library access. So you can search on PLOS on either of our names and find papers that have the details of the optics.
Yeah, so everything's pretty inexpensive. So if you wanted to build your own, you totally could.
Yeah, I've been fascinated with just the holographic microscopes just in general and where they're headed. Actually, I will just interject my own quick question for you two about, what's your hope for holographic microscopy in like the next 10 years and where you're hoping to see it get to?
I just wrote a proposal to send it to the International Space Station, so I'm super excited about this. We'd like to see how microgravity affects bacterial swimming, and there's a lot of other people interested in that as well, and not currently an instrument on the ISS that's good for that. So we're super excited about this.
Yeah, and I'm interested in seeing it get into a lot of water quality investigations, both like freshwater and seawater, and also for potential drinking water applications or medical process stream analysis, so you can look at things on the fly.
Awesome. All right, Matt, if you want to give us our next question from YouTube. All right, Jenny asks, that was great, thank you. Question, how do you catalog or keep track of your micrometeorites?
So I have a little booklet that I made, and I have, I can show you really quick here. So I have, this is where I keep them. I don't know if we can get in there, kinda. So there's 20. There's 20 in each circle. So there's 100 on each thing, and I know their numbers. Each one will have a number, and I'll write down the age of the roof that it was on, the location, as much information as I can about that, and then I'll just store that away. So I have a bunch of them just sitting right there, and you can kind of see them.
That's awesome. Do you ever lose track of them and get frustrated?
Well, I've never lost track of them. I have it pretty solid where I know where they are, but I have lost them right here at this location. So I will take the most powerful magnet I can find, and I'll go digging around in my carpet to try and retrieve it, which has actually been successful once or twice. So
I can only imagine how devastating that feels to lose a micrometeorite.
It's pretty bad. I've been wanting to get these, like amazing images lately, and I lost a really beautiful one, and I've been trying to find it. It's around here somewhere. I don't know.
Some of the troubles of being a microscopist. All right, next question for us. From another Lena. Some physiochemical systems can display motility, lipid droplets, for example. How do you distinguish between biological motility from similar behaviors displayed by non-biological phenomenon?
That's a great question. That's why I'm a physicist and not a biologist, is because there is a lot of physics involved in that question, and a lot of looking at non-biological systems, things like Janus particles, quantifying Brownian motion, and a lot of just quantification of these motility properties in order to make sure, absolutely sure, that we can prove that something is displaying meaningful biological motion and not motion related to just non-biological processes. And I would say most of the time you can quantify by speed, directional changes, and so forth that you've got biological behavior, but there are certainly exceptions. There are both false positives and false negatives, and this is something that my students are doing PhDs on.
Yeah, and I'll add a couple things. Because we're doing basically capturing the electric field or the perturbations in the electric field that the object that goes through are and how it perturbs that before it shows up on our detector, we actually can extract the index of refraction from what we're looking at rather than just an image. So we get both the index of refraction and the intensity image, and you can use that to determine whether things are likely alive or not alive. That there's a kind of big gap between things that have water-like density and things that have mineral-like density, and there's not a lot of things in the space between about 1.35 or 1.4 and about 1.7-ish index of refraction. And so that's additional information that we get for free as a byproduct of how we do the imaging, so we can discriminate biological from non-biological.
Great. And a reminder to all of you watching on YouTube, you can ask more questions in the YouTube live chat. We've got time. So if you want to ask any more questions or anything, please go ahead and enter those and we will get to them. Matt, please go ahead and bring up our next YouTube question from Danielle. Scott, can you tell us more about those metal beads? What are they? Why are they?
Sure. They're pretty amazing. So if you think about the unmelted micrometeorite or micrometeoroid out in space, it's made up of all these different things, and there's metal within it, and there's all the other compounds that are in it. And as it comes into the atmosphere and it heats up, the heavier elements will kind of solidify in the center, but they'll have more momentum, so they'll want to keep going. And sometimes they'll completely come out, or sometimes they'll get basically just frozen in the micrometeorite, and then they'll be sticking out. So it's kind of a good detector when you're starting to look for micrometeorites. If you see that metal bead, it's more likely going to be a true micrometeorite. But yeah, they're pretty gorgeous when I'm able to take a decent photo of them.
Yeah. So a question I had for all of you was about, for some people watching this, they're going to be like, I get everything. This all makes sense. This is all really cool. For other people, this is going to feel a little bit technically overwhelming. Microscopes, despite being something that's fairly ubiquitously used in a lot of different settings, can be a little bit intimidating sometimes. And I wanted to ask each of you about, if you remember back to when you were getting started and working with microscopes and doing the type of work that you're doing with them, what was sort of like the hardest part you remember when you were getting started? And a sub question to that, what was someone, some resource that was really helpful to you? So Jay, do you want to start? What was sort of something that was hard for you when you were getting started with microscopes, and what was something that you found really helpful?
So I think the hardest part is kind of always the sample prep, getting the right sample, getting it to slow down. And so when I was a kid, I discovered Carolina Biological Supply Company, and they had a product called Proto Slow. And I was so excited by this, and it was just a couple dollars, but it was just some cellulose liquid that you add to your slide, and it will slow your protozoa down to the point where you can see them. So before that, all I could see was things zipping around, and little did I know that there's this special product to slow things down. So discovering fixatives and dyes and stains and hanging drop slides and all of these sample prep tools is wonderful and has followed me throughout my career, because as I've gone into other types of microscopy, all of these tools just become even more complex and interesting.
Yeah, that's a really good one. I haven't used ProtoSlow yet myself, but it has been recommended for me. And there's definitely been times where I probably should have used it just to like get those little critters to slow down a little bit and be able to see them a bit better. So that's a really great tip. Chris, what about you?
Yeah, I came to microscopy kind of late, so I've always used microscopes on and off. The hardest thing was always just finding small things in the field of view that you put them on the stage, and then you've got this tiny thing and you've got a lens that you can't see, and you have to get everything around, and it's easy to shoot past what you're looking for. And it's really just a lot of patience and a lot of getting used to making smaller and smaller and smaller motions with your fingers so that you can make just a tiny amount of motion. And it's really just the patience of dealing with the tiny things.
Yeah, you are 100% correct. And I always find it hilarious that I am now the president of a microscopical society and doing a lot of microscope stuff because I am a very impatient person. So it's definitely always very a big test for me to work with microscopes because it requires a lot of patience. And admittedly, I don't have it, but I'm still going for it, and it probably teaches me to, to mellow out a little bit more, which is probably good. Scott, what about you?
So the hardest part for me, especially when I started looking for micrometeorites, is there just wasn't any information out there. I'm one of the first people in the world to find them, so trying to find the information to begin with was just filled with incorrect things. When I first started, I remember I read like an article, and it said you can go up on your roof, and anything you find that's magnetic is a meteorite. So I went up on my roof, found a meteorite right away. I was extremely happy. And then later, yeah, a little small, but then I later found out that they had to be spherical. So then I went around and I found all these spherical things, and then I was like, all right, now I have micrometeorites. But it turns out that those aren't micrometeorites either. So basically, once I found John Larson's book and he kind of became my mentor, that was when everything changed. And the information that he was able to share, and just it's kind of a catch-22 in a sense. The best way to find micrometeorites is to actually know what they look like in person. So if you know somebody who has one, or if you can find your first one, then it becomes a lot easier. But trying to figure out what that first one looks like, that's the hard part.
Yeah, and this is one of the reasons why I love that, the San Francisco Microscopical Society exists, is because so often microscopy knowledge is not always well shared. And a lot of times you just have to find people who have more experience than you or have tried out things before you have, and just be like, is this what I'm looking for? And so often still a lot of knowledge is just stuck in networking with people and getting to know communities and people who are willing to share, and having communities that are willing to share is really useful. I certainly remember like your micrometeorite hunt, when I started looking for tardigrades for the very first time years ago, I put some soil underneath the microscope and I saw something move around and I was like, that's definitely a tardigrade. It was a rotifer. Nowadays, I would not mistake a rotifer for a tardigrade, but there was a time where I did, and without kind of talking to people and knowing what to look for, it was a bit harder. So yeah, you are spot on. So I have a final question for all of you before we wrap up the event. Microscopes are really fantastic tools. And if you're like me, it's kind of changed your perspective a little bit. So I wanted to ask each of you about, how microscopes have changed kind of how you view either existence or the planet or outer space or any of that. Have you had sort of like a change in perspective through using microscopes over time? Scott.
So I think I might repeat it again, but I'm obsessed, right? So now that I know what micrometeorites are, it's basically all I think about. So when I'm outside, I'm thinking right next to me. I've walked along this road for a long time and never thought once about what it was laying right next to me or what could have been right there. But now I know that they're all around us everywhere. So if I can just kind of narrow it down, get rid of the noise and find out where they are, it's a big help.
Yeah. Chris, what about you?
Yeah, really very similar. So I came at this from building astronomical instruments and doing low temperature physics. and not really thinking about the really tiny things that are just everywhere around us, and you don't think about them and you don't see them, and then building a microscope that is designed to find living things at the lowest possible concentrations, and then starting to find stuff at really low concentrations. Like, whoa, there's a lot of stuff out there that we just don't see and that we don't think about, and it's just everywhere. And even in water that looks totally clean, you can find stuff at detectable concentrations. It's just really remarkable how much stuff there is around.
Jay, what about you?
I'm prepared to bow down to our microbial overlords. So microbes are the dominant life forms on the planet and probably on other planets too. And so I've spent a lot of time trying to envision what Earth looked like before anything larger than an E. coli evolved. And there was life for 1 billion years without anything bigger. So there are probably many planets like that. And it really kind of stretches the mind to envision that. And the other thing that was kind of funny is that when coronavirus came around, there were all these deniers. And somebody posted something like, how can you be afraid of something you can't see? And my first thought was, of course you can see it. It's huge.
Absolutely. Yeah, it just changes your perspective all around. Well, thank you all so much for being speakers tonight. This was fantastic. And I'm sure you've got everyone else's minds spinning around with cool ideas and thoughts. So thank you all for being here.
Thank you.
Thanks for having us.
That was awesome.
All right. And with that, I wanted to we will have the recording of this event on the same YouTube URL that you are on now. So if you're watching the live stream, you can just copy paste this YouTube link to share with friends. The recording will be up. And also to remind you all that the San Francisco Microscopical Society has open membership to anyone. You can go to the link at the bottom. Membership is $12 a year. A reminder that if you are a student, we offer students who are currently enrolled a free first year to the Microscopical Society. So just send us an email and we'll send you the special link for students for that. But with that, that wraps up tonight. And I just had a fantastic time. I hope you did too. I wanted to, again, thank all of our speakers tonight. Also, all of our fantastic volunteers and the San Francisco Microscopical Society board. It's entirely a volunteer organization at the moment. And there's so many people that go into making this happen. So thanks to all of you who have been putting in time to be a part of the society. And if you're interested in being part of the society, you can go to our website, send us an email. We are happy to hear from you. And also a thanks to Matt, who is our AV guy backstage, who's been running this whole thing while I'm up here speaking. So thanks to everyone. And I hope you all have a fantastic evening and have a bunch of geeky dreams about microscopic stuff. Good night.